Yes.
So I noticed that for our first project, it was themed around like essentially glorified injection attack.
Yeah.
Working with the equipment. So is there going to be like another theme for the second project?
So the second project, I will, the keys have done the work on it, given to me. I'm going to put it up on the website this week. That'll be out on Thursday. Is web security attacks. So it will be a totally different set of attacks based on sort of SQL injection, cross-site scripting, things like that. But the theme is still attacking. The theme is still getting your code into somebody else, to some extent getting your code to run in somebody else's system. But you will not be dealing with GDB and assembly code for this one. So for people who appreciate that, that's a good thing. For people who liked it, that's a bad thing. Yes?
Will it be beneficial to do that homework before the exam?
It's always beneficial to do homework. I think looking through it and thinking about it will certainly, I always think that practicing things you learn in lecture are helpful for the exam. And so I would say yes, but I also would say there's a lot of other material also to cover, and so you have to sort of figure out how to spend your time. Is there a question over here? Yeah.
Is this going to be like JavaScript or?
To be honest, I don't remember. Because again, the ETAs have been sort of taking the lead on developing this. And so they need what they developed, and I need to go through it. But it does not rely on sort of being a amazing programmer and web programming technology. Yes. Yes, we'll cover hardware security at the end of the semester. So after we're finished with web security today, we're going to move into cryptography and protocols, and then later in the semester we'll come back to hardware. I felt like doing the low-level injection attacks followed by even lower-level hardware attacks would sort of like kill people in a way. Just sort of be down at that low level for so long, and so I wanted to kind of split it apart a bit. To sort of, pop up to nice high level, scripting languages, HTML, SQL, things like that for a while. But yes, we will come back. There was an interesting paper that Google published this past week saying that everything is fundamentally insecure, and there's no way to make it secure. So because there's this hardware attack called Spectre and Meltdown, and the key thing that Spectre does is Spectre lets any program read just about anything in memory whenever it wants to. So if you ever have anything secret in memory, you can't protect it if somebody else can run code on your system. For example, if you run any web pages that have JavaScript, which you all do, that JavaScript can read almost anything on your computer if it really wants to. And the Google engineer said this is sort of fundamentally almost impossible to solve. So you should all feel confident about that. But that's the kind of attack we'll get to later in the semester. Any other questions? Yes?
Before the exam, will we get an answer key to the study questions, or will we
No.
have like some sort of stamp model?
No, but you're welcome to discuss them with other people. You're welcome to email me and ask questions. Hopefully you're welcome to sort of Google and look online for answers. We will do some. I'm trying to think the best. I feel like probably next Tuesday in class, I'll spend part of the class doing a review and answering questions for everybody. Okay, so we're talking about web security. We had just talked about vulnerabilities in PHP at the end of last lecture, and we're about to start SQL injection attacks and cross-site scripting attacks, sort of high-level attacks on websites. So before I do that, I do want to talk about an attack that came out. I just read about this morning. So it basically says, yet again, things aren't secure. So you might have heard about cloud computing. In most cloud computing environments, they give you a virtual machine to run, where you provide an operating system. If you want, some places will give you what's called a bare metal server, which basically means they just give you a server with none of their software running on it. And on that server, you can put your own hypervisor if you want, a virtual machine monitor, your own virtual machines. You're guaranteed nobody else is using it, so nobody else can be spying on what you're doing, so it should be more secure. But the problem is that pretty much every machine has what's called firmware in it. And this is very low-level code that sort of configures the hardware. So for example, the question is like, how does your operating system get onto some machine in a data center? Well, there's some firmware that knows how to read code over the network and start running it, called the BMC firmware. And so somebody figured out that this BMC firmware, you could actually find bugs in it and subvert it. So when you run one of these bare metal machines and run your operating system on it, you can overwrite the firmware with your own firmware, which will then do things like tell you who was using it beforehand, that could potentially break into other virtual code that's running later and tell you things that it's doing. And so it means that you can also potentially change it. Normally when you reboot a machine, it zeroes out all of memory. You could modify it so it wouldn't zero memory out, so you could see what was in memory the last time somebody was using this machine. So this is kind of bad. And this is, I think, demonstrated on IBM's cloud. And they have some blog post about what they're doing it. Now, the reason this happened is there was a bug in the firmware that allowed it to be overwritten. It's not a design feature that when somebody rents you a server, you can replace the firmware. So this is due to, buffer overflow style bugs, things like that, in the existing firmware that meant that you could sort of trick it to letting itself be modified. So this is why we work on security. Okay, so here's sort of the topic list for the day. I think I mentioned these before. So we're going to start off with SQL. I'm suspecting some of you have taken 564 and C databases before. But if you haven't, SQL is the language for getting data into databases and out of databases. And what's interesting is that most of the programming you do is with APIs, where you call an API to read from a file, write from a file, send to a network, receive from a network. See, databases are different in that you actually write programs as strings, and you give the whole program as a string to the database to execute on your behalf. So here is a basic SQL command. The first where it says select company, country. This is saying we want to find these columns in a database table that is named customers, and we want to pick out entries where the country is not the USA. So the idea is we want to find all the companies in our customer list that are not from the United States. Another command you can say is drop table, which is also delete. So this will delete the table customers. So you can see these are nice strings, and as we know, strings are evil. So you can sort of get you might have this sort of unpleasant feeling in your body right now saying, uh-oh, I see some strings on the screen, bad things are going to happen here. There should be some eerie music. So how do you use this in a language if you're writing a website? Well, you might do something like this, where first you might do is read this recipient field that somebody posted to your website. You would then construct the query string, select person ID from the person table where the username is this recipient. And then you would say execute this query. So the key thing here is that you're building a query string in your server-side programming language, and then you are submitting that whole string to SQL. You are not sort of passing an API where you construct some data structure that represents the query. It's really just a string. So far, so good. So another thing you might do here is here's some programming language. This is ASP, Active Server Pages used by Microsoft. And one thing you might do to log somebody in is write SQL query to directly see if this user exists. So in this query, we're going to say execute the query, select star, star means return all the fields, all the columns in the database that match from users, where user equals, and we're going to pass in the user field that the user provided to the website, and the password equals the password. So this will look to see if there's a user and password that match and return all the information. And so we say if not, if it's not end of file, meaning that this means there was some data returned, then log in a success, otherwise it will fail. So seems like a relatively reasonable way to check passwords if you are storing clear text passwords in your database, which let's not talk about that. Any questions on this SQL and the code here? So there's a variety of different scripting languages people use. I was using PHP, I'm using ASP now, but they're all sort of, fairly readable code. So the challenge is, if I as the user can provide input that just gets concatenated into the string, then I can actually insert extra SQL commands into that command string. I'm not limited to providing just the field they said I was supposed to provide. So for example, suppose that I provide for the username a closing quote and then or 1 equals 1. Right? So the or 1 equals 1 is not really my username, it's another piece of SQL command, and what it does is it means that the command that is actually given to SQL, which is just string concatenation, is select star from users where user equals double quotes or 1 equals 1 and password equals whatever. And so what this means is that I have just said now return all the users, right? Because or 1 equals 1 is true, and so this condition user equals quote quote or 1 equals 1, that piece is always true. So this will now match on every single user in the database. This is probably not what the programmer intended, but what we have done is we have injected some SQL code into the query that they produced because they weren't very careful with their inputs. So in this case, because the result doesn't actually just says was anything returned, if there's anything that has the password that I provided here, there's one more thing here which I forgot to mention. So you see the dash dash there. I forgot about this. The dash dash is sort of like 2 slashes in C or a hash mark in a scripting language that says ignore everything after this. So what this says is or 1 equals 1 dash dash, which means everything else in the line becomes a comment. And so the check to find the correct password is commented out. So our query really is just this beginning piece now that says select a user with no name or 1 equals 1, returns everything. Our code will check for end of file. Since we're returning all the users in the database, you can log in. So be warned. So the other thing you can do, though, is you can inject arbitrary command, and databases are really very programmable things where you can, ask them to execute command. So, for example, this is a SQL injection that runs on a Windows machine where you're saying execute a command shell. This is starting a command window, and then pass it this command line: net user bad guy, bad password like add. This is the command line in Windows to create a new user with account with a password. So you can get SQL to run arbitrary code as the SQL account, which might be running with administrative privileges. The other thing you can do if you want to be more malicious and annoying is you can say drop table users. So while it's logging you in, you can tell it to delete the table of users, which will then block everybody else from logging in. So you can wreak a lot of havoc with this. So needless to say, people pick up on this. XKCD, the favorite comic of most computer scientists. I'll let you look at that for a minute. So the key thing here is really what it says at the end. I hope you're going to sanitize your database inputs. Right? The problem here is that we are taking data from the user just as we didn't sanitize inputs in buffer overflows. We didn't check that they were the right size for our inputs. The problem here is we're taking inputs and we're not checking they're the right format, right? The programmer clearly expects a username just to be a username and not arbitrary characters. And so things are happening that they didn't expect to happen because SQL just takes these strings. So this is one of in a way, this is an incredibly powerful attack because you can do so much with it. So 43 million credit cards were stolen because of a SQL injection attack where somebody could just sort of read databases, information out of a database. This basically made the card systems company go out of business because who would trust a company that lets things like this happen? Lady Gaga's website was hacked and the information about her fans were stolen because of a SQL injection attack. So this is a very common problem, and when you hear about lots and lots of information being stolen, a lot of times it happens from a SQL injection attack because it lets you get access to sort of everything in the database that you can attack. So what can you do about this? So as I mentioned, the key is really to sanitize things. You don't want to just use string appending to construct your command. You want to use tools your language provides, such as parameterized queries if you have them. So a parameterized query sort of tells the database, here's the query string, and then you provide the parameters separately. So in this example, we are saying, this username has this, we're going to sort of put in a template that says it's some variable at user, and the password is at password, and then we're going to add the parameters separately. So the database now sees the string, and it sees the parameters separately, and the database now knows that this is exactly just how it fits in here, and there's no question of it sort of providing extra SQL commands that can execute. So the thing to note, and I shouldn't advance so far, is that the general thing you want to do as a programmer is to look at the inputs and see, do they conform to your expectations? Are there extra SQL commands? Are there double hyphens in a row? Are there spaces in the input where you don't expect spaces? Are there semicolons, quote marks, anything that really shouldn't be there in the field? In a field, you want to strip that out. And most programming languages for writing web servers have ways of stripping the input to sort of say this really should only be text, it shouldn't be HTML, shouldn't be JavaScript, shouldn't be SQL. So any questions on SQL injection? In the paper that was on the reading list, there's a lot more information of other things you can do. For example, ways that you can figure out what are the different fields in the table. Because a lot of times you might have been to a website where it'll actually print out the error message from the database when you can't connect. If it does that, some databases will do things like reprint the query string, and will tell you this query string is bad, and here's sort of the place where it went bad. So you can see the original query string so you know how to modify it. Other databases will tell you, this field doesn't exist, or this field is in the wrong position, which will let you figure out the names of the columns in the database. So using SQL injection, you can both figure out what's in the database you're attacking, and how to get information out of it, and how to manipulate it. Okay, so that was a quick preview, or not a preview, but you could spend 3 days just on SQL injection if you wanted to. So we're going to move to another web server attack. This is called cross-site request forgery, CSRF or XSRF, and we touched on this earlier. So in this attack, we're going to go to a legitimate server. We're going to establish a session. We're then going to, for some reason, visit an attack server. The attack server will send us some malicious information, and that malicious information will cause us to send a forge request to the good server using our cookies. So the idea is that the malicious server can make us do something to a good server using our session information. We mentioned before how you can do this if you can sniff somebody's session cookie by monitoring network traffic. So this works even over encrypted channels because we are making a legitimate browser client send a legitimate request. The problem is the request didn't come from the user. The request came from some other web page. So the definition of a cross-site request forgery is when an attacker disrupts the integrity of a user session with a legitimate website by injecting networking requests, communication requests from the browser. So the nice thing is you can do this, as we mentioned before, with our timing example, to sort of look at web pages behind a firewall. So if I'm logged into some University of Wisconsin website, for example, for setting your grades, and then I visit your malicious website, you could potentially cause my web browser to talk to a grade database server at Wisconsin only and submit a request to change your grade if you pull this off. Even though that other server, the web server, is not on the internet accessible to the attacker because we're going through the browser client. The other thing to note is that because we're using the victim's cookies, we get to use the victim's information. So if we send a request to purchase something from Amazon, we're going to do it on their account. Or we can also cause, as we mentioned before, the victim to use the attacker's credentials, for example, to connect to something, and, so we can start tracking their behavior to sort of see their history. So the basic element of many of these styles of attacks is one of the first things we have to do is to get a victim to come to our website. So one way to do this is to send some email, some phishing email, click here for, enter a contest to win an iPad, click here to update your Adobe Flash player, something like that. In this case, we control the whole web page. The other thing you can do is you can post to a public forum where there's comments, and you can put some script on that public web page that goes to the attacker website. So for example, in my graduate class, students, when they read papers, they have to post a review of the paper as a comment on a blog. And what I see is a lot of spammers will be posting comments that are actually script commands that will try to get, that will, if you load them, will run that script automatically and would cause anybody viewing the web page, because the script is embedded in a comment, if they viewed that comment, their browser would go to the attacker website without the user even knowing. So this is a challenge of public forums that allow you to sort of provide arbitrary HTML, because they could do things like, just a link that somebody could click on, or if they allow scripting, you can sort of make the browser do things automatically. So this is the first stage, is getting somebody to go to the attacker. So then the second thing is that we're going to provide from the attacker website some kind of form, and the form will have a submission page that will go to the legitimate place. Now, as an attacker, I'm allowed to provide HTML. The HTML I provide can cause the user, can't have links to other websites, which is legitimate. So in this case, I'm going to have a form where the action will be that we'll visit the bank and we will transfer money from the user's account to the bad guy account. And then I'm going to add some scripting. So a form alone isn't bad, but with scripting, I can say, actually submit this form automatically without the user doing anything. Right? So a web page is totally legitimate to have a form in it. Web pages can definitely link to other web pages. That's fine. Web pages can have scripts in it to go and fetch things. So what is the problem with having code like this? Where does everything break down? Because it seems like this is exactly what the web is supposed to do, right? You can have forms, you can have links, you can have scripting. Where did security break down? Any thoughts? Well, let's think. Suppose that I ran this script and I was not logged into the bank at all. And I ran the script. What would happen with this script? Nothing would happen, because when I went to the bank and I said, transfer money, the bank would say, you're not logged in, you don't have an account, you can't do anything. If I'm logged in, though, yes.
Is this form on the site that's not picked up?
This form is provided by the attacker.
So like it has a different origin.
So it has a different origin. Right, so the website cannot directly sort of, from scripting, the script code can't directly send requests, but here it's a form that it's submitting to send a request. So it's a little bit different. But so if I'm logged in here, then when I send this request, then the request will actually happen. And so the key problem here is that the scripting code is asking me to do something using my cookies and my session information, which is different than what the attacker can do on their own. So the attacker is causing my browser to use my cookies for that website to do something. And that is what people have figured out is the flaw here, which is it's okay if an attacker sends you to some link or causes you, fetches data from some place, but it should do that as the attacker or with the attacker's information. It shouldn't be able to cause you to go someplace and use your cookies to get there. Right? Because you didn't actually choose to visit the bank and make this request, so there's no reason that you should use your cookies when you visit it. So the reason we send this is because the browser says, oh, you're visiting the bank. We've got cookies for the bank. There's these scoping rules that say when you visit the bank, these are the cookies we should send. So the browser isn't really aware that it's doing this on behalf of an attacker when it's sending the cookies. So here's sort of an example how this works. So the victim browser goes to the attacker sends this form, and it can be invisible for you so you can't even see it once the script is submitted. The form, when you run the script, will actually do the post using the session cookie stored from the victim browser to the bank. The bank will say, great, we just transferred $100 to the attacker. And as you can see, these is where the user credentials fit in. Yes?
I didn't know how the attacker gets access to your cookies,
Okay, so the question is, how does the attacker get access to your cookies? So the first thing is, you visit the attacker web page for some reason. Either you get there on your own, you clicked on a link, or there was some script that the attacker provided on another web page. Okay, do you believe that part? Okay, so then the attacker will provide this snippet of code here with this form and this script that causes the form to be submitted. So this is the malicious content the attacker provides. Your browser will run this. Now the cookie rules in your browser say, when you visit a website, apply the scoping rules for any cookies you have stored and send those cookies to the website. So this session ID cookie here is provided by the bank, stored by your client browser, and the browser knows whenever I visit bank.com, I'm going to look for all the cookies from bank.com and send the appropriate cookies. And so the browser is just applying the totally normal browser rules of when to send cookies. And the rules don't say anything about why you visited bank.com, whether the user typed in the URL bank.com, whether you did Google bank.com, Google for the bank, and you clicked on a link at Google, whether you got an email from the bank and clicked on a link in your email program. And so to some extent, like when you run Gmail, you've got a web browser there can be a link for bank.com there. You click on the link, you go to bank.com, and it should get your cookies. So this is not, from the browser's perspective, this is not all that different than that situation. Yes?
So the same origin policy doesn't work.
Right. The same origin policy doesn't apply here because it's totally, the thing that the attacker is doing is totally reasonable to do. I believe. So the other thing, so that was just submitting a form. You can do the same thing to log in. So here the action is to log in. So here we are sort of forcing someone to log into Google with the attacker's credentials. And once they run this form, they will send the request to Google to log in. Google will send an OK with the session cookie, and then anything the browser does, for example, search for llamas, will go using this Google session cookie and will be recorded in the user's account. And so the attacker can now see your search history through Google because you're now using the attacker's account. If you log into Gmail, though, as a user, you probably discovered this problem. Okay, so what do we do about it? So one thing we can do is we can say, as a web page, we really sort of the same origin policy idea. We can say we really think forms should only be submitted from our web pages. A form to us should never come from some other web page. So what we will do is we will, in every piece of HTML we send back, we'll give a secret validation token, some random number that's not guessable. And whenever you submit a form, we are going to append this secret validation token in the data that we're sending back so the web server can check it. So the attacker doesn't know this secret. When they submit a form, they don't know this information, they can't provide it. But the programmer does, the real website does, so this is visible. This is one defense. Any thoughts on that? So in a way, it's sort of like a cookie, but it is provided explicitly through the HTML code or the JavaScript instead of being stored and provided by the browser automatically. So the web page is sort of in control of it. The challenge with this is it sort of makes you rewrite your web pages to actually do different things, so it's harder to actually pull this off. You have to worry about if this session ID is ever sent over the network in clear text, you know, somebody could potentially take this session ID and launch an attack if they can see it. So it's not a perfect solution. Another thing you can do is you can look at the referrer field. So if you remember when we talked about HTTP, one of the fields in the HTTP header is the referrer that says what URL sent you to this web page. So this would mean that when you go to log in at Facebook, it could see, were you referred by a facebook.com web page or did you come from someplace else? In the case of an attacker, the referrer would be the attacker's web page or the blog where they posted the script or something like that, and not a facebook.com or bank.com web page. So the referrer field would sort of show the correct information. So to some extent, this seems like a nice idea. But again, as you can tell, because it's not the last one on the page, it's not a great idea. And the problem is that the web is broken. And so there's a bunch of places where that referrer field can get removed. So to some extent, there's a privacy issue that you may not always want to show websites where you're coming from. And so you might have like a privacy extension in your browser that removes this referrer field. There are web proxies that companies use to sort of pass information securely out of the web page, out of the internal network that strip off the referrer field. And so it turns out that the referrer field is either not available or not correct in a lot of cases. So if we rely on the referrer field, we're going to break the web. And one of the rules of web security is you can't break the web. The other thing you can do when you're doing requests is you can add a custom HTML header, and you can have your script in code sort of provide the right header, again with some kind of secret cookie or something like this. And you can do this. The challenge is, again, it gets complicated. You have to sort of use a particular framework to make requests. So how does this work? So secret validation token, if we go into more detail, is we are going to have some random number that we encrypt with a key the server knows. When the server gets the validation token back later, it can decrypt that token, see if it's a token that it produced. So the token can't be seen. This is where the same origin policy comes in. That applies to JavaScript. This token value is in the DOM, the document object model. So it's available to JavaScript code for the website, but not available to any other websites to see. So the attacker.com can't see this. So that's what it works. So this is an example of referrer validation, where the attacker is coming from the, where we check that. So this is how referrer validation would work when you go to the bank. If it's referred from bank.com, it's good. If it's referred from attacker.com, it's bad. The challenge is, it comes up, if it's blank, what do you do? Because it's blank a lot, you can either let somebody log in, which means you're pretty easily subverted, or you can block everybody from logging in, which means a quarter of your customers can't log in anymore. So, bad choices. Okay. So this is the custom header, and so this means that you basically write an API in JavaScript to make requests instead of using standard HTML forms, and this request sort of embeds special information. So Google has a web toolkit for doing this, where it will use a special header, and here the header doesn't necessarily have to have a secret, but because you have to have this web toolkit, it means that only your clients will use the right web toolkit to actually communicate with you. So this works, but it means that, again, you have to modify your code, as I mentioned. You can't just use standard HTML forms anymore, which are kind of convenient for a lot of things. And it doesn't work across domains. So if you have multiple domains at your website, this may not work, because if the header is sort of tied to a particular domain. So this solution is okay, but it's sort of cumbersome. So the challenge here is there's nothing that's really great. So that's a summary of cross-site request forgery. You sort of saw how it worked of tricking somebody and a couple of different solutions on how to address it. Any questions on it before we go to cross-site scripting? Okay, so cross-site scripting is when a website tricks the client into running a script that abuses some other client. And there's a couple ones. One is when you visit one website that causes you to do something on another website. Another one is when you actually store information, and when the user retrieves that information later, they will sort of do the wrong thing. So you can think about if there's some information that you can, as an attacker, upload to a website that it stores, like a comment on a blog or something like that. When some other user visits that legitimate website, it will see the malicious content and do the malicious activity. So let's see how this works. So in this case, you're going to visit some website, attacker website. You receive a malicious link. That malicious link that you click on, this might be, so this comes from on a web page controlled by the attacker server. You click on that link, it goes to the victim server. So the key here is that we are providing special information to the victim server that is malicious. This is the trick to the attack. So that step 3, when we're calling the victim server, is providing bogus input to the victim server. The victim server will then produce a web page that has content that came from that request. So something in that link to the server provided data that the attacker controls. So when you as a user get this information back and you see it on your web page, it looks like it was provided by the victim server. As a good user, you click on this interesting looking link, and that interesting looking link will actually do the wrong thing and send the valuable data back to the attacker. So this is a way an attacker can sort of get you to pull your information out of one server and send it back to the attacker. So the challenge here, which is again, deals with strings. The problem is when we have some code here, this is in PHP, we are going to be in the web code, in the HTML that we respond with from a website, we are actually echoing an input from the user. So this is how the attack happens, right? Because we're going to echo what the user provided here. So if we can manipulate this term field on the input, then we can make the output HTML have extra things in it that shouldn't. So for example, suppose I provide this term here as the input, right? It's not just the term you search for, it's actually a snippet of code. Some scripting code that says open a window and send the cookie to the website and send the document cookie. So the key thing here is when this script runs, what web page does it run on? Does it run on the bad guy's web page or the victim's web page? The victim's web page, which means, according to the same origin policy, it has access to all of the victim website information and page information through the DOM and all the victim's cookies. And so what this will do is this window will open and it will send all the cookies for this web page to the attacker. Right? And so the key thing here is this is on a web page from the victim, and so it has that. So that is how we're doing cross-site scripting, because the attacker is causing the victim to produce some HTML and JavaScript that runs as the victim that will cause the victim to leak information back to the attacker. So here it is, sort of on the network. You visit the attacker. The attacker is going to have this on a page somewhere. So the attacker sends back some web page. You click somewhere on the web page, or maybe it's scripted. In this case, it might be scripted that you click on here. So when the user clicks on this link, it will send this parameter to the victim server. The victim server will send back this HTML results for, and then it will have the script. And it's because we inserted that term verbatim. We didn't sanitize it in any way. And the script here will then release information back to the attacker. Any questions on how this basic attack works? No. Okay, so that attack required that you actually visit the attacker website to do this, but that's not always the case. So I remember the other case I mentioned is where the attacker can store information on the victim machine. So in this case, the attacker is going to inject a malicious script into the server victim. Again, some information that the user victim will actually see, such as a blog post, a blog response, an entry in a username in a database or something like that. Anything that I can provide that the web server will later show to you, and you will sort of run as the server's code. So for example, a comment on a blog. So I have seen this quite a bit on my blog. Something like this, where there's some review and then there's a script that will run a piece of JavaScript code that steals all my cookies. And so the problem is that scripts are run automatically even if you don't click on the link. So if the blog software allows you to provide HTML in your comments and it allows you to have scripts, then as the client browser accessing this, you will say, oh, this came from the blog website. I trust Mike. He's a good guy. He's got good blog software. I'm just going to run all the scripts. And these scripts, because they run as the blog server, have access to all the blog server information and will send all that information off to the attacker. Yes?
Why would a web page allow HTML comments or tags?
So the problem is that if you do nothing, right, if you just have a text box and you let people type in anything you want and you save it as a comment, and then when you push comments later, you just take whatever people entered and plug it into your HTML without sanitizing it, this is the behavior you get.
Okay.
So good blog software will have the option of stripping out any HTML tags or stripping out, only allowing a subset of like markup HTML tags. But if you don't actively strip things out, this is the behavior you get. And so the key is you really need to actively look at all your inputs and make sure they're in the format you expect and not code that's going to manipulate the browser client. So the other problem is as the browser client, it's hard to defend against this. It's really the website that has to defend against this. Because the website is the entity that allowed the malicious scripts onto that website. As a browser client, you can't tell whether the HTML you download from that server is legitimate HTML or it's something bogus that an attacker provided. So, as I mentioned, what do you do about this? The number one rule in all of these attacks is never trust your users, right? Whatever input they provide, you should sanitize it, make sure that it doesn't have HTML tags, doesn't have JavaScript, doesn't have SQL in it. You can also, quote things, put quotes around it so that it's very clear. Put quotes in a way that can't be replaced, for example, by stripping quotes out of the input, so that whatever they do provide can't actually ever run as code. You can also do output filtering, so you can allow any input you want, but when you actually generate HTML, you can strip out things that are not regular text in your output. You can also simply allow sort of only a subset of HTML, B, underline, U, things like that for formatting, but nothing else. The other thing you can do is there are some things you can do on a client. So one of the things we actually mentioned it a little bit earlier was this notion of an HTTP-only cookie. An HTTP-only cookie says the only time you can send this cookie is when a user actually clicks on a link. It can never be sent because somebody scripted access. So if there's JavaScript that says, I can't go back, but if the JavaScript that said, send our cookies to the attacker, that is JavaScript, that's not HTTP. And so the cookie is marked as we can't send it because of JavaScript. And so the cookie doesn't get sent in that case. When you actually fetch a whole web page, when you're actually fetching a web page from the server, it would go, but you can't see that cookie unless it's as part of getting a web page. So it's not available inside JavaScript anymore. So this is sort of still a problem because so much of it depends on web servers doing the right thing. So these attacks sort of keep on popping up every once in a while. Any questions on cross-site scripting? Yeah.
So I don't totally understand why it's not a same origin policy issue because you're accessing a different origin using a script.
So the problem is that unfortunately I can't go back while I'm recording. So what we're sending back, the HTML we send back is not actually a script. It's just It is just a, actually, there was a script to open a window there. But we're not, the same origin policy is really about what can you navigate and what can you access. And so the same origin policy says if you have JavaScript code, you can't access the DOM from web pages with a different origin. Here, the only web page we're looking at is the web page of the victim. And the JavaScript code comes from the victim, and so that JavaScript code is allowed to see everything on the victim's web page. But JavaScript is allowed to make arbitrary HTTP requests to visit places, because you might need to go fetch, an image from someone. If you think about a standard web page with an image, you might embed an image from some other website. And so you need to be able to do that, to embed images from other locations, or else the web page. And so for that reason, we can't sort of stop a web page from having a link that embeds something from some other website. So the same origin policy is really about what can JavaScript see in memory. Other questions? Okay, so what is the fundamental quick quiz? What do you have to have in your code to be vulnerable? What is sort of the sign that you have code that is vulnerable to cross-site scripting? What should you look for in your code? Yes.
For it to be vulnerable, unsanitized string, right? Or unsanitized info.
Okay, so, but to be specifically vulnerable to cross-site scripting, what do you have to do with those unsanitized inputs? Any thoughts? Anyone else? So it's true, you have to have unsanitized inputs, but you have to do something very specific with them. Yes.
That means the DOM.
Well, the inputs go into the DOM already. So the inputs from the user go into the DOM that the server can see. The DOM is on the client. So you need to, I guess what you're saying is they need to get into the DOM in the browser of the web page. So you provide some unsanitized inputs up to the server. The server then, the key thing is the server has to echo them back to the client somehow. So you have to, as an attacker, get stuff, inject stuff into the web server. The server then sends back as part of a valid, legitimate web page to some client. The client will then see those unsanitized inputs and execute them. So the key is if you ever take user input and copy it back and send it back to the user. For example, if there's a website you go to where you enter your email address, and you click submit, and the next web page shows you your email address. Or when you enter your username, and then there's a validation page that says, here's your username, here's your password. That is the kind of code that can be vulnerable if it doesn't sanitize the inputs. Is there a question over here?
Just answer a question.
Okay.
So I think in the server side, they should filter out the HTML tag.
Right. Right. If you don't want to allow HTML explicitly, you should filter out. If you want to allow HTML, you should sort of restrict it to a subset of things that you think are safe, such as no links, no scripting, things like that.